Okay, so yeah, so completeness, you can rank any two indifference curve. Non-cessation implies that the upper or the right-hand side indifference curve gives you a higher happiness. And from the non-transitivity, we can prove that any two indifference curves cannot cross each other. So the proof goes by the proof by contradiction. Uh, so suppose there are two indifference curves that are crossing each other. If they cross each other, then there'll be uh, this a common point B. But if you have a common point B, then um, you're indifferent between A and B, and you're indifferent between B and C. But that will imply that you're indifferent between A and C. So that's a contradiction, right? Because we started with a two different indifference curve, but what you arrive at is that these two indifference curve give you the same happiness. That means they are not two separate indifference curves, they are the same indifference curve. So we prove that two indifference curves cannot cross each other. All right, so we know that under the assumption of non-satiation, or in a broader term, we sometimes call it monotonicity, in the sense that the more you have, the happier you become. So anyway, so in the under the assumption of non-satiation, we learned that the indifference curve is downward sloping, right? So if I get more of the first good, then you're willing to sacrifice some of the second good, right? So that's what I meant by the downward sloping indifference curve. Um, but there are two kinds of downward sloping indifference curve, right? So you can think of the this kind of indifference curve, the first graph, or this kind of indifference curve, the last graph, right? So in the first indifference curve, um, the indifference curve is convex, right? And the last indifference curve, the indifference curve is concave, right? And what are more likely? Okay, so let's think about that. Which is more likely, right? So let's say so x1 is say water, and x2 is a bread. Okay, so let's suppose that's the case. Then what do you get is the following. So suppose you have lots of water but very little bread. Okay, so let's say you have lots of water but very little of the bread. Okay, so you're very hungry but you have plenty of the fluids, right? So someone comes to you and say that I'm gonna give you a little bit of a bread, and what did you say? That's gonna make you much happier, right? Because you have very little bread, and someone is offering a little bit of bread, so that's gonna make you very happier. So in the units of water, you would be willing to sacrifice lots of water for a small amount of bread, right? So in other words, you're willing to sacrifice lots of the water for the compensation of a little amount of the bread, right? So in that sense, this is so that's kind of the thing you would do, right? But in the last graph, what it says is that so the same water for the first good and the bread for the second good. What it says is to sacrifice. Um, so the last graph says you're willing to sacrifice very little amount of water for a very large amount of bread, right? So that's quite unlikely situation, right? So you have lots of water and you have very little bread, and someone comes to you and say that I'm gonna give you lots of bread. How much are you willing to sacrifice? How much water are you willing to sacrifice? And your answer is very little. That's very unlikely situation, right? So that's probably is not going to be the uh, good picture of what happens in the real world, right? So we conclude that the first picture is more likely the situation than the last graph, right? I mean, of course, I'm not saying that the first picture is always the case. I mean, we can definitely think of the um, the last case. So what would be an example of the last case? Um, I know. So, um, well, we can think of addiction, for example, right? So let's say the first axis is, I don't know, what are you addicted to? Um, um, I know, what are you addicted to? Okay, smoking. So let's say you're smoking a lot of cigarettes, right? Okay. Um, and um, and the second good is, I don't know, let's say, I don't know, something else. And you're so much addicted to the cigarette, and then so if I take a little bit of a cigarette, then um, you want to be compensated by loss of the second good. Um, yeah, well, but yeah, it doesn't really work with the addiction, but yeah, sort of thing. I know. What's another example? Okay, one another example I can think of is so let's say so the second good is Android phone, and the first good is iPhone. Okay, so I should say iOS. Okay, so most of the cases we are here or there, right? So you use only the iPhone or you use only the Android, right? So but let's say we can consume them fractionally. So let's say 23 hours of a day I use iPhone, but 1 hour of a day I use Android phone. Okay, so if that's the case, the indifference curve might look like this, right? Because if you're giving up, so let's say you need to use your phone. So let's say you're addicted to using uh, a mobile phone, okay, a smartphone, right? So if I take a little bit of so let's say you have an iPhone initially, and I take some of um, hours of using the iPhone, then since you're addicted to using the smartphone, um, you get some withdrawal effect, right? So for that, I need to compensate you with the different phone. It's an Android phone, but I know maybe you don't know how to use the Android phone, or you feel so much uncomfortable using the Android phone, or it takes a longer time to do the same thing with the Android phone because you're not used to it. So that's why you might want to be compensated by loss of hours of use of an Android phone. Okay, so that might be an example. Okay, I'm not saying the third case is never a possibility. We can definitely think of a situation where the indifference curve looks like the third graph, but in most of the sensible cases, the indifference curve will look like the first graph. Okay, so unless mentioned otherwise, we'll stick with the first graph. Okay, so we are going to assume the first graph, unlike in most of the cases, unless it's mentioned otherwise. Okay. And the middle graph will be even a strange thing. So it's like it's normal here, but once you get past to a certain point, it becomes a weird relation between x1 and x2. Okay, all right. And this let's talk about the satiation once more. Um, so 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 what kind of indifference curve look like this? So I'll give you a story. So the first indifference curve is this is often called perfect complementarity case. Okay, so the boring example is the Englishman drinking tea. And that's the example I learned when I was reading the textbook long time ago. So let's say x1 is tea and x2 is a sugar. Okay, and this Englishman is very particular about the tea. Okay, so for him, the ratio between the tea and the sugar has to be perfect. Otherwise, it's completely ruined and you don't want to drink it anymore. Okay, so let's say the ratio is 1 unit to 2 units. Okay, so for each unit of the tea, you need 2 units of the sugar. Okay, and if you have more units of the sugar, right? So say you have 1 unit of the tea, but you have 4 units of the sugar, then the extra unit of the sugar, extra 2 units of the sugar, doesn't mean anything to you because you need exact ratio of 1 unit of the tea and 2 units of the sugar. Any extra is doesn't add anything, so you probably want to throw them away. Okay, so in that sense, these two blue points will give you the same happiness. Okay, so if you think of this green dot, it's a similar story. So at the green dot, you have 2 units of the tea and the 2 units of sugar, right? But you need only the perfect ratio, 1 unit of the tea and 2 units of the sugar. So having an extra unit of the tea doesn't do anything because if you just make a tea without the sugar, it's just a complete ruins for you because you really care about the perfect tea. So basically, it's not gonna make you happier anymore at all. So you probably wanna just throw away the extra unit of the tea. Okay, so they're gonna be just um, yeah. So in that sense, this this very particular this picky Englishman's preference is represented by this L-shaped indifference curve. Okay, this is L-shaped indifference curve. All right. All right. So this would be an example of a perfect complementarity. And the second example, so this is so this indifference curve is represented by the circle, and this arrow is representing the more happiness. Okay, so if you follow the arrow, this person is becoming happier and happier. Okay, and once you arrive at the center, at this point, there is no other way you can be happier, right? So this is sometimes called the bliss point. Okay, so this is like bliss means like a perfect, complete happiness or something. So you're so happy, there's no other way to make you happier. All right. So this is like the best point. So what will be an example of this kind of um, indifference curve? Okay. So so you can think of the x1 as say humidity and x2 as a temperature. Okay. So you can think of the humidity or the temperature as a consumption. So in the sense that when I'm choosing an allocation where I'm not allocation, location. I mean, when I'm choosing a location where to live at, I'm choosing a temperature and humidity, right? So, so that's in that sense, we can treat this weather as a consumption good. Okay. So remember, everything can be considered as a consumption good, even the service, location, temperature, humidity, and traffic, anything. Okay, so this is so you probably don't want to live in a very humid location, but you don't want to live in a very dry. Why do I keep saying allocation? All right, sorry. So you don't want to live in a very humid location, and you don't want to live in a very dry location either, because well, I mean, you think the living in a dry location is good, but that makes your skin very dry and itchy sometimes. Okay, and also sometimes too cold when it's yeah um, and in terms of temperature, you don't want to live in a place where it's too cold, or you don't want to live in a place where it's too um, hot. Okay, so I used to live in England for 5 years. So England is like and in terms of temperature wise, I think I liked it. It's not too hot, not too cold. I mean, it's too cold. Maybe it's a little bit chilly for certain people, but I like that kind of weather. So, but it's really humid. It is raining a lot. The part of England I used to live in was somewhere like here. Right? It is very humid, but the temperature wise, it is okay. I also used to live in LA, Los Angeles, for 5 years. It's a really dry place. It's like so dry. So even when the outside temperature is, say, almost 30 degrees, it's if it's almost 30 degrees, it's really hot in Korea during summer, right? Because the humidity is so huge, right? So high. But in LA, humidity is so high so that even if the temperature is really high, if you're in the shade, you don't feel like it's too hot. So being in the shade is enough to avoid the high temperature. So actually, I didn't have the air conditioner when I was living in LA because it was never hot inside the house. So the LA I used to live in was like here. So it's like, but it's very dry. So like the skin condition was not so good. I mean, also it was very sunny. So um, and I was too lazy to use the sun cream. Um, so now um, I'm living in Seoul, as you know, and Seoul is even crazier places like here or there, and going back and forth. There is no spring, there is no autumn. It's just between the scorching hot, humid summer or scorching cold and extremely dry winter and going back and forth. It's like in terms of the temperature and humidity, it's a pretty extreme place, I guess. Yeah. All right. Okay. Now we're going to introduce this elasticity of substitution. Um, this concept is difficult to understand when you first see it, but later I'm going to come back to this elasticity of substitution later once we finish a part of consumer theory, and then why we need this kind of thing will become more or less apparent. But for now, it's going to be a little bit difficult. So first of all, before I talk about the elasticity of the substitution, I'll talk about just the elasticity. Okay, so elasticity is capturing a relation between the two variables. Okay, so so let's think of the two variables y and x. Okay, and you want to capture the relation between x and y. So So how are you going to do that? So one thing you can do is when x changes by a certain unit, how many units of y need to change or changes, right? So that will be the basic setup, right? So so an example is the x is so let's say interest rate, and y is say unemployment. Okay, so it's a bit boring economics example, but you can think of that example, right? All right. So 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 what's going to be unit for this one? So unit for this one will be so let's move it a little bit. So in this case, the units will be with uh, percent point. It's going to be a percent point over, so unit will be percent point over percent point. Right, so this is not a good example. Um, yeah, but this is yeah. So all right, so let's forget it. Let's use a more interesting example. Um, so x is I know my life is so boring, so I cannot think of an interesting example. So um, all right, so let's say you're playing a certain computer game, and x is hours of a play. All right, and then if you play this computer game, um, you get expensive items from. So the longer you play, you get more expensive item. Okay, so I mean, of course, the chance that you're getting this expensive computer game item is not. Um, um, I mean, it is a bit random, but let's ignore that for now. So let's say we simply say the more you play, the more expensive item you get. So Y is the dollar amount of the value of of an item you get. Okay. So in that case, the units for the delta Y over delta X will be hour per. I'm sorry, will be dollar per hours, right? So that will be the unit of the delta Y of delta X. So maybe this is okay, but um, having the unit is sometimes makes a problem in terms of comparing two different things. Um, so for example, to get the certain game items, one way to get the item will be increasing the hours of a play. But another thing you can think of is that if you're more skillful in terms of playing the game, maybe it takes less time to get the items, right? So 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 we can think of this kind different um, different variables and x, y, and x and z. So x is the same thing, but we can think of z as a skill, right? Um, right. So we can think of that way. So so you sometimes want to compare the two, right? So having more skill is more useful in terms of getting expensive item, or having or spending more time is more important to getting an expensive item, and so on, right? So having units in a certain measure is sometimes not ideal. So sometimes you want to have it sometimes you won't have this measure not to have any unit. So what do I mean by not to have any unit? So you can think of this way. Okay, so if you think of that way, this is unitless. So this is unitless. It doesn't have any unit. So what it measures is that when x increases by 1%, so let's say x was 200 hours in the first place, okay? So you're spending 200 hours every month, and say you increase the playing hours by 2 hours, that means you increase the x by 1%, okay? So as a result of a 1% increase of playing hours, how much y has increased? But here, y is also measured in the percentage, right? So let's say you used to make $500. Now, by increase of the 2 hours of extra play, um, so let's say you get $10 more, right? So that means your revenue has increased by 2%, right? So that will be 2% over 1%. So that will be, so the units of the percent in the numerator and the denominator, they cancel out each other. So this becomes just a 2 without any unit, okay? Because it's a percentage versus a percentage. So so this just becomes a 2, right? Without unit. So we can think of it. So in general, this is called the elasticity. 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 Uh, uh, I don't know, for or of. Yeah. So in general, this is called the elasticity. So you represent a certain variable's percent change against a percent changes of the other good. Okay. So this elasticity gives us an idea how convex an indifference curve is. So for example, if the indifference curve looks like this, as you see here, the percent change from the good x to the percent change of good y changes a lot. Okay, so when you change from x to from here to there, so let's say this is delta x, and let's say this is delta y, and you can see that delta y over delta x is yeah, well, I mean, I guess I have to give you two graphs to compare them. Okay, so let's think of two cases. Okay, okay, or okay, okay, so this is almost a straight line. Okay, um, okay, yeah. So these two graphs are gonna be different graphs, right? So I want to use this okay, okay. So let me see. Okay, so I want to distinguish these two graphs. So one thing you observe is that the MRS changes a lot in the first graph, right? But in the second graph, the MRS doesn't change much, right? So if the so when you change certain amount of x and certain amount of y by the same by the same magnitudes, and if the MRS change doesn't much, then it's a flatter indifference curve. If the MRS changes a lot, then it's quite a convex. It's a more convex indifference curve, right? So by looking at how much x1 and x and y changes versus the change of the MRS, we can have a coefficient describing a shape of an indifference curve. So so what you do here is that you draw straight line like that. Okay. So these two straight lines have the same slope. Okay. So say this slope is 1/2, and let's say this slope is let's say 3. Okay. And when slope changes from 1/2 to 3, how much does the MRS change? So that will be a measure, right? So if it's large, then that means it's a very convex indifference curve, right? So that will be a way to look at this elasticity of the substitution. But well, of course, the elasticity of substitution is defined. What's going on with my pen? Defined as the percent change in the ratio of x2 and x1 over percent change of the MRS. So that's like the inverse of what I have done, right? But you know, it's so that means if sigma, if the elasticity of the substitution is large, that means percent change in MRS. So I should write down percent change in the MRS and percent change in the ratio of the second good and the first good. So these are the inverse, right? So this is the equality. So you can always think about this thing and not this one, this ratio, and think about the inverse of it. Then I don't know, at least that's how I understand the elasticity of the substitution, right? So when the ratio changes by the same amount, what's the change of the MRS? So in the first graph, the change of the MRS in the percentage is higher than the percent change in the MRS on the right-hand side graph, right? So I can conclude that this one is large on the left-hand side, but elasticity of substitution is the inverse of it. So that means the elasticity on the left-hand side is gonna be actually smaller than the right-hand side. Okay. Well, I mean, I should think of the absolute value, not to be confused about the negative and the positive. All right. So I'll give you an example. So let's see. So 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 we can think of some example like linear indifference curves. So how does it look like? So the linear indifference curve is like that, right? So here, when the ratio of the second good consumption against the first consumption changes, the MRS doesn't change at all, right? So in other words, the percent change in MRS against percent change in the ratio of the consumption of x2 against x1 is simply 0. So in other words, the elasticity is infinity. Okay, so this will be the elasticity of the linear indifference curve, and so perfect complementarity case. So the indifference curve is going to look like that. So so this is a little bit trickier. So if you compare these 2 points on the same line, we arrive at the same conclusion that the elasticity is as infinity, right? If you think of the 2 different points in another part of the straight line, we're going to arrive at the same conclusion because MRS doesn't change. But if you think of the 2 points on 2 different linear parts of the indifference curve, you can see that the MRS changes infinity, right? So in the lower one, MRS was 0, but now the MRS is infinity, right? So the change of the MRS is also going to be infinity. So in other words, percent change in the MRS against the percent change in the composition of x2 over x1, that's going to be infinity, right? So that means the elasticity is going to be actually 0, right? So that's the perfect complementarity case, right? So we talked about the linear indifference curve and perfect complementarity case. And constant elasticity of the substitution. So what does it mean? Um, so probably I should have explained it earlier, but you know, these elasticities concept is based on the differentiation, right? And differentiation is a description of a point, not a description of the 2 points. Although in the 2 graphs, I explained it as if the concept is about the 2 points. But to be precise, I mean, roughly speaking, we can think of the 2 points on the same indifference curve. But to be exactly uh, um, right, the concept is based on the calculus differentiation, so that the concept is defined on the points. So we can think of computing the elasticity at the 2 different points, and in general, they're not the same. In general, they're not the same. But sometimes with a certain class of indifference curve, we can think of the case where the elasticities are the same everywhere. Okay, so whichever points you choose, elasticities are the same. I mean, not only that, we can think of different indifference curves. So I know, maybe we can think of this way. So 3, 4, 5, okay? So all right, so we can think of so this is constant elasticity of the substitution if all these 6 are the same. Okay, so in fact, pick any points on the consumption set, it gives you the same elasticity of the substitution. That kind of indifference curve, that kind of set of indifference curve is said that to have a constant elasticity of substitution. Okay, so simply we sometimes call it CES preference. Okay, Remember that preference is not represented by a single indifference curve. Preference is represented by the set of indifference curves, right? So, yeah. So to be able to say constant elasticity of substitution preference, I need to give full set of indifference curves, okay? And on which the elasticity of the substitution at every point should be the same, right? Um, so once we get to the utility function, I will be able to give you an example of a constant elasticity of the substitution preference. But for now, I'm just going to say it in words, okay? So that's it. All right. All right, so now we're going to talk about the utility function. I'm sure you heard of this word, the utility function, many, many times in the past, um, even from high school. Well, but I never used that word until now, okay? So, but now, finally, we're going to employ this concept of the utility function, right? All right, let's take 5 minutes break.